All right, guys, so I understand that electron configurations can be a confusing topic. I promise they're not actually that confusing. It's just sometimes the way that we express it as a class doesn't fully make sense until we start looking at it one-on-one. So hopefully this video helps a little bit. It seems like when I worked with people one-on-one and explained it a little bit like this, it has been making more sense. So hopefully you guys got your periodic table colored and labeled. We have our S block, our P block, our D block, and our F block down at the bottom. And then hopefully you've labeled them. So we should start at 1 and go all the way down to 7S. Over here we have 2P, and we go all the way down to 7P. We have 3D, 4D, 5D, and 6D, and then 4F and 5F. So I think it would be, excuse the bell, I think it would be helpful for you guys to write down these numbers if you haven't done so already. I think it will make a lot more sense when we actually start writing these electron configurations out to have them in front of you. So basically the point of these electron configurations is we're trying to illustrate our lowest possible energy arrangement of those electrons. Because if we go back to our Heisenberg uncertainty principle, we're saying in that we cannot at the same time know how fast an electron is moving and also its location. And so if we can't say we know its location at all times, we can predict an approximate region. And so what all of these orbitals are showing us, so again, 1s, 3p, all of these numbers express orbitals. Our number in front of it is expressing how far away from that nucleus we are. The further away from the nucleus we get, the further, or I should say the greater our number is going to be. And then our letter is illustrating shape. And so I think a lot of words that get thrown around are shell and subshell, but it doesn't really help you guys when you don't really know what those actually are expressing. So number tells you how far away from the nucleus you are. The letter gives you that orbital kind of shape. And so S would be our sphere, P is a dumbbell shape, D is kind of a 4-leaf clover, and F is going to be a kind of a combination of D and P. So if we start, I think a good point would be to also acknowledge that 1S up here, that is going to be our lowest energy location, or I should say lowest energy orbital. And then down here at 7p, I'll put it right over here, is going to be our highest energy. And so we're always filling those orbitals from lowest to highest. And so we're always going to be taking this systematically. We're going to start at 1s. We always move left to right across of our periodic table as we start filling up those electrons. So again, we're trying to locate where those electrons are. And so we can't have every electron sitting super close to the nucleus, or else that's going to be way too much energy. We don't want that. Our atom's not going to be very happy in that state because everything's kind of crowded. If you guys remember, if we have too much negative charge close together, they're going to split just because of those like charges. So we first want to go, put a number 1 across that periodic table. After we have gone across that periodic table, we go down a row, so I'll put that as number 2. And then we pass through that 2s orbital, and then we go across to our 2p. Once we go through there, we go down to 3p, across, down, all the way across, down, all the way across. We go down to 6s. I'll explain in a second where we go from here. We don't go straight to 5d, we go to 4f, and then we go to 5d all the way across to 6p, and same thing for our 7s, 5f, 6p, and 7p. Anyways, where we would go from here, I think maybe a good thing to write out is our s orbitals can only have a maximum of 2 electrons. We can't have any more than 2 electrons in that region of space. Doesn't matter how big it is, again, due to energy, the only number of electrons that could be in those s orbitals are 1 if we are half filled, or 2 if we have a maximum. Our P is going to have a maximum of 6 electrons, D block will have a maximum of 10, and F will have a maximum of 14 electrons. And so we could verify this by looking at the periodic table. We organize that periodic table based on energy and based on how many electrons could go in each orbital. So if we look, if S orbital has a maximum of 2 electrons, 1s would have hydrogen, helium, so 1 and 2. 1, 2, 1, 2, 1, 2, 1, 2, and all the way down. P, if we can only have a maximum of 6 electrons, 1, 2, 3, 4, 5, 6. And same thing for all of the P block orbitals. D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F, if we have 14, 1 all the way over to 14 here. Yes, I had you guys color the entire F block the same color. I will tell you guys that our F orbitals end here. This column here is technically D1. So that would be 5D1 and 6D1. You guys might get to a point where we practice that a little bit. Just keep in mind that atomic number 71 and 103 at the end of that F block is technically not F block, it's D block. Sometimes it's organized this way just because the properties of these two elements more closely matches the ones in our F block. We'll get more into that when we talk about periodic table. If we go here and here in these two boxes, these are all D1. So basically it says 57 to 71. We'd go here all the way over. Again, that last number is 71. This one's 89 to 103. We go down, 89 is here. We go all the way over to 103. 103 starts our D block again. Anyways, we'll start with an example, neon. So neon has 10 electrons. Its atomic number is 10. We're assuming that everything here is neutral. And so we have the same number of protons and not neutrons, same number of protons and electrons. So those charges cancel out, we're neutral. So if we have 10 electrons, we need to figure out what we're trying to do with this entire process is map out where those electrons exactly are located. So again, they can't all be together. There's too much electron-electron repulsions there with those negative charges. And so they have to fill very particular energy locations in order to have the least amount of energy strain. So again, we always want to start with the lowest energy. We're trying to find the lowest energy configuration. So we always want to start up here at 1s. For any element, again, start at 1s. So we'll write down 1s. We got 2 electrons, 1, 2 electrons. So we write down 2. And then we still have 8 more electrons to account for because we've figured out where those 2 are going to be. We still have 8 more. So then we've gone all the way across the periodic table. There's nowhere else to go in this row. So where do we go now? We'd want to go down to the next row. So we start with 2s. Let's write that down. We'd start filling up that 2s orbital. Again, s orbitals can only have a maximum of 2. So 1, 2. We'll write that down. And so now total, we've mapped out 4 electrons of those 10. We still have 6 more we need to account for. So that's where we go across that periodic table. We have another orbital. It's called 2p. And so we'll write down 2p. And then we count 1, 2, 3, 4, 5, 6. So we've gotten to our neon. That's the one that we're looking for. So we're going to stop there. We're not going to continue. We have 6 electrons. We'll put that here. And this right here is our electron configuration for neon. I did attach a video to Google Classroom. They kind of went through it in a way that for some people is helpful, but I think illustrating it with this periodic table is going to be a lot more helpful for some of y'all, or most of y'all, I should say. So again, we've gotten to 10. We could stop. If we count our electrons, we got 2 plus 2 plus 6. That's 10 electrons. We could verify that. Neon's atomic number is 10. 10 electrons. Basically what this is illustrating, I only want you to know how to write it out. However, what might help illustrate what we are exactly trying to do here, if we are assuming that our nucleus is that dot in the middle, if 1s orbitals are a sphere, it might be kind of hard for you to see. Let me see if I could zoom in. If our 1s orbitals are a sphere, we would have 2 electrons in there. Again, we can't have more than that because we're gonna have too many electrons competing for space. And so where we would go from there, again, if we said we have to start filling that 2s orbital, there's gonna be a second sphere around that first one that has higher energy and it's further away from that nucleus. So that's gonna be 2s. We're gonna have 2 electrons in that outer sphere. We still need to account for those 6 electrons, and we said that they were in 2p. 2p kind of looks something like this. Each of those dumbbell shapes are a configuration of that p orbital. So there's 3 p orbital configurations on a 3D XY z-axis plane. So again, this is in 3 dimensions. And so what we end up seeing is our neon molecule is going to look something like that. Again, I don't need you to know or be able to fully visualize what those molecules look like. I could do it off the top of my head just because I've been working with this stuff for years. But basically, let me add that in, 2p. But the importance of why we're doing this mapping out of our electrons right here is because it tells us what that molecule looks like. And so we've been, since kind of the beginning of the year, been trying to illustrate what do our atoms look like. And so we've gone through different models. We've gone through Dalton, we've gone to Rutherford, we've gone to the Bohr model where we have those rings, and we're all saying that those aren't entirely accurate. This is the most accurate that we have, at least at this level, that we'll cover. And so these are our electron clouds with our orbitals illustrating where those electrons are. Again, we can't know exactly where they are. What these regions of space show us are where those electrons are most likely to be. So hopefully that helps. I guess before I end this video, there's also something called a noble gas configuration. And what this is, it's trying to give us a shorthand method, because if I tell you to map out lead, your, real quick, your electron configuration is going to be as follows. 2p6, s2, 3p6. Again, this is for lead. Its symbol is Pb. That's a really, really long electron configuration. So what we're trying to do is make it something shorter. So if we're at lead, what we're doing is we could write down the noble gas that comes before it. Our noble gases is everything in this last column. So everything in this column 18, everything in this last column is a noble gas. Those are the most stable because its electron, or its valence shell, has full electrons. So these are very stable atoms. But basically what we could do, if we go up one row and then go all the way over to our noble gas, we land on something called xenon. If we write down xenon in brackets, we're assuming we know the electron configuration for everything that comes before xenon. We're assuming we already know that. So we write that down in the box. We've accounted, therefore, for 54 electrons. 54. However, lead has 82, and so we need to also account for the other remaining electrons that aren't included in that 54. And so we start at xenon, we've written that down. We now go to 6s, and we would fill it in as normal. So we go to 6s, and then we jump down to 4f, 14. Then we come back to 5d, 5d10, and then 6p, 2. And so if we compare, that's super long. That one's a little bit more manageable. And so it's just an easier way of writing those out. The most important thing in all of these electron configurations is that highest energy orbital that each of these elements has. That is going to have a huge impact on how it's going to bond with other things around it. So that's kind of why it's important. But hopefully this helps. If you guys have more questions, let me know. But hopefully that is enough to get you guys started on these electron configurations.